So, does somebody have the answer now?
Is it because silver and chloride ions make like an oxidizer and a reducer?
No, that's not it, but at least you're thinking about it. That's good. Well, anyway, we don't have too much time. It's because silver chloride is much more stable than silver ion alone. And so it's the stability of the product. It's making a more stable product. Well, let's continue here. So we have silver and we have water, and so let's compare. We can't use the silver with the chloride. We have to use that silver up there. Silver is not terribly reactive. That's why it's called a coinage metal. A lot of the other metals are much more reactive. But when we compare it to water, here we have water. We have water up there too. We already know this is water better because the product is more stable. And so H2O is a reducer, but it's not a very good one. And so it turns out the strongest reducing agent is silver. Okay. And then what we do is we're going to copy the equations off the chart. And so copy the equations. Let's see, this will be 4. And add them together.
Wait, Professor, I have a question.
Uh-huh.
Can you explain what side we're looking at? Like when we're seeing how we use the chart, what side?
Well, we use both sides. You know, if you look at this chart, you could call this a chart of oxidizers because fluorine's at the top of the chart here, top left. If we have a table of oxidizers, don't we also need a table of reducers? And so we should have a chart of the oxidizers and what it forms, and a chart of the reducers and what they form, right? And so we should have 2 charts. But it turns out, because of the conjugate relationship, we don't need 2 charts. We only need 1 chart. Because if the oxidizer is strong, its conjugate is going to be weak. And so here, fluorine's the strongest oxidizer, which means fluoride, its conjugate, which is a reducer, is the weakest. It's the weakest because fluoride does not want to lose electrons. That makes sense because if fluorine has such a strong pull, such a strong attraction for electrons, it's not going to lose those electrons easily. And so once fluorine has gained that electron, it makes something stable, fluoride. And so when we read a table like this, we always go, we can read it in any direction. Like I said, it doesn't matter if I flip it, right? The thing is, you can't get disoriented. You cannot get disoriented if you know 2 things. What 2 things you need to know in order to avoid disorientation? Right. And so if I threw it on this chart, would you get confused? Left and right is totally irrelevant to me. I don't care. Left, right, upside down, or up, down. It doesn't matter because I just know lithium and fluorine. And so this chart's very easy for me to read because there's lithium, so this must be all the reducing agents, and fluorine must be on the other side. Where's fluorine? Down here. Here's fluorine. And so when I look at this chart, I go any way. It doesn't matter. Left, right, it doesn't matter. And so when I'm looking at this, I just pick whatever side. Now, the trick here is water. Water occurs on both sides. A lot of people, when they look at these charts, they don't spend any time really looking at them. And so they miss things. They miss things that are like amphoteric. You know, water goes both ways, oxidizer and reducer. What else? Can you name one other species that can either act as an oxidizer or reducer? One other species. This is blurry. Maybe I'm going to do a different. Let me find a better chart here. I don't like this chart because that chart was good until the 90s sometime. And then everybody decided, they don't want that chart. They flipped it upside down. And so the chart in your book is going to look like what I just showed you, or like this. This is even worse. I have it. I have a chart that I'll show you. I'll just use this chart. And so, yeah, what other species? Well, you got to look at the chart once in a while. Take a look, and once you get familiar with the chart, then things will become more clear. Mm-hmm.
Are you going to give us this chart like this?
Mm-hmm. Not this one, the one out of your book. Actually, the one out of your book is kind of long. It's in Appendix D. It's pretty comprehensive. I think it's about 5 pages long. So I'm going to give you a shortened version of that chart. It's actually from chapter 21, I think, which you don't have, so I'll print it out and give it to you. You can look, what you want to do is you want to get more familiar with the chart. How do you get more familiar? You just look at it, go through each entry like we were doing the other day. That's it. If you do something as simple as that, you're already a step ahead of a lot of people. A lot of people don't even bother doing that. A lot of people, they see that chart, it just looks like just a jumble of letters and numbers. Forget it. It doesn't register at all. Be surprised at how, doing little simple things like that can make a big difference in how you do. Well, here, you don't need to know any chemistry to use this chart method. We just copy the equation. So we look for the equation for silver. So I go down and I look for silver. And I copy the equation down. Should I just copy? Oops, shoot. This is this touch screen deal. Should I just copy the equation as written? Silver ion plus an electron? No. I'm going to write it backwards. But it doesn't matter, forward, backwards, because it's all irrelevant. It's going to be silver solid goes to silver ion plus an electron, which is the reverse of this reaction. Why did I just reverse this reaction? The reason I reversed this reaction is because I don't have any silver ion, right, as a reactant. My reactant is silver metal. If I wrote this reaction as it was given on that chart, then I'm wrong because there's no silver ion present. Is that one of the inventoried items? No. Therefore, it's not a reactant. However, nitrate is, so I'll just write that as is, near the top there. Near the top, I got nitrate plus 4H plus 3 electrons yields NO gas plus 2 H2O liquids. And so I just copy down those equations. Okay, this part might be tricky, but it shouldn't be. Here we're forming 1 electron, here we're consuming 3 electrons, and so the electrons aren't balanced. So what do we do next? We're going to balance the electrons by multiplying this one by 3. And so what we end up with is this. We end up with 3 silver metals plus nitrate plus 4H plus This is going to produce, consume and produce 3 electrons, so the electrons will cancel, they must. It's going to produce 3 silver ions plus NO gas, nitrogen monoxide, plus 2 H2O liquids, nitric oxide, it's called. All right, this is the most likely reaction to occur. The next step is we need to determine a driving force. What is the driving force for this reaction? Well, what is a driving force? Tell me what a driving force is. I'm sorry?
What causes the reaction to happen?
Yeah, causes the reactions to happen. And so what do all driving forces kind of have in common? What's a characteristic property of the driving force, would you say? I mean, why does it cause a reaction to happen? Uh-huh.
The product side is more stable.
Yeah, good. Yeah, product side is more stable. And so here, what are we looking for? Are we looking for gas formation? We have a gas form. Is that a driving force? Yes or no? Gas formation, is that a driving force in chemical reactions? Yes, it's a driving force in chemical reactions. Well, not all chemical reactions. There's a driving force in metathesis reactions. It's not a driving force in redox reactions. The reason why I divided the chemical reactions into the types that I did was to keep the driving forces the same. If we stuck with combination reactions, you know, we had redox combination, acid-base combination, and metathesis combination. And so we had 3 subcategories of combination reactions that each would have their own individual driving force, which is a hassle. You know, do you want to memorize 3 subcategories of combination and 3 subcategories of decomposition? No. And so what we are doing is we're just separating out the reactions based on driving force. All redox reactions have the same driving force, and what is that driving force? Well, it's forming something more stable. So what do you look for in terms of stability in redox reactions? Stronger to weak, good. Stronger to weak what? Yeah, perfect. Stronger to weaker oxidizing agent and reducing agent. And so we got to figure out what the oxidizing agents are. We want to go from stronger to weaker, a combination. This is a competition between reactants and products. So if the products are more stable, then we expect driving force. If the reactants are more stable, then it's uphill battle and we expect no reaction, right? And so what we're going to do is we're going to look in terms of oxidizing agent and reducing agent. So it's a competition between the reactant side and the product side to see, because we know this. The stronger the oxidizing agent is, the more stable or the less stable it is. The less stable. So the stronger the oxidizer, the less stable. And so that makes sense. Stronger to weaker. We're going from less stable. Weaker oxidizer would be more stable, right? Less reactive. And so we got to figure out, well, what is the oxidizer here? We already figured it out, right? We figured it out because nitrate and H+, that's our oxidizer. Silver is our reducer. But the trick is, now we got to take this backwards. And if we were to reverse this reaction, what's the oxidizer and what's the reducer going backwards? Well, the easiest place to determine that is not in the net redox. The easiest place to determine what the oxidizer and the reducer in the reverse direction, what they are in the reverse direction, the easiest place is the half reactions. So fortunately I left the half reactions and didn't erase them. And so when I look at silver ion here, is it an oxidizer or a reducer going backwards? It's an oxidizer because it's taking electrons, it's gaining electrons here. You have to be careful because, you know, sometimes you get it mixed up because oil rig, have you heard of oil rig? Oxidation is loss. Oxidation is loss, but here oxidation is gain. We're gaining electron, right? And the reason is because this is an oxidizing agent. An oxidizing agent can make something else become oxidized. You know? An oxidizing agent. And so is the oxidizing agent oxidized? No. That is the robber thief robbed? No, the robber thief robs somebody else, right? And so you can think of the oxidizing agent as taking electrons from somebody else. And so that's what's happening here. And so this is the oxidizing agent. This here is what it's taking electrons from, because this, going backwards, this is going to give up electrons here. So this is going to be the reducing agent, a combination of NO gas and H2O liquid. And so we compare the oxidizing agent here and the reducing agent here. And so we try to figure out which side's more stable. How do we determine which side's more stable? We look at the chart. And so go back over to the chart and take a look at the chart and see. Let's compare the two oxidizing agents because those occur on the left. The two oxidizing agents are a competition between nitric acid versus silver ion. Who's stronger, nitric acid or silver ion? And so looking at the chart, we go from fluorine down. What's the first one we hit? Nitric acid. Silver ion is just below here, but silver ion is weaker. And so nitric acid is stronger. So you get an S. Silver ion is weaker, so W. Well, because of the conjugate relationship, you know, if the oxidizer is like this, the reducers must be like this. And so the reducers, this has got to be stronger, this has got to be weaker. Let's confirm that just to make sure nothing's wrong here. And so we start off at lithium, then work our way up. And the first reducing agent we hit is silver metal. Here's silver metal here. And then as we continue up, we will see NO and H2O here. Oops. Here, NO and H2O, here's silver metal. This resolution is pretty bad. We'll switch the chart pretty soon. All right, so that's our driving force. And so we do have a driving force here, and we should have reaction occur. Now, in single replacement, we didn't predict reaction will occur. We predicted no reaction will occur. And so the chart method can be used. It can be used not just for single replacement style reactions, but it can be used for all redox reactions. You know, all redox reactions that occur on the chart, we should be able to figure out. But is this chart comprehensive? Well, no, because you have a more comprehensive chart in your book, right? And so these charts are bridged. You know, they contain the most common species, right, that you'll encounter. But sometimes you're expected to do a little more.